Okay, thank you. Yeah, I'm going to talk about some of the models that we've developed to understand convection-driven MHD in the limit of rapid rotation. A lot of this work was done by Stefano as a postdoc at CU, this work, and Meredith Plumley was a former grad student here at CU, now a postdoc at ETH. And collaborators Keith Julian, Steve Tobias, and Philippe Marti. So why do we care about rapidly rotating MHD? This is a movie showing the Earth's magnetic field, the radial component of this magnetic field for about the past 400 years. And the thing that you'll notice is that it's moving around a lot. It's dynamic. It also has a strongly dipolar field, very large-scale field. And we know from theoretical investigations that rotation plays a fundamental role in the generation of global-scale magnetic fields for both planets and stars, and our work kind of builds upon this as well. But this is a regime that is notoriously difficult for study with direct numerical simulations, which has been a constant theme throughout this workshop. We can understand this a little bit more in our dimensionless parameter space. So on the vertical axis, I'm showing the Reynolds number. Horizontal, I'm showing the Ekman number. I can plot a line of constant Rossby number here, just arbitrarily chosen to be Rossby number of 0.1. We can call this regime down here rapidly rotating. So below this line is rapidly rotating. It's low Ekman number. Above this, we could call a weakly rotating regime, provided the Rossby number is not too large. And our problem here is that planets and stars are in this regime down here, laboratory experiments, numerical simulations, et cetera, kind of high on the high Ekman number regime. It's difficult to stay in this rapidly rotating regime while pushing to higher Reynolds numbers. Right? So this is the ongoing problem we have. The asymptotic models that I'm talking about, which are an extension of what Keith Julian presented on Monday, they live in this regime of rapid rotation. Okay, so they're in this asymptotic limit of small Ekman number. We can increase the Reynolds number by driving the flow harder and harder. A few details about the model. We're going to simplify things quite a bit. We're not going to talk about the sphere for now. We're just looking at a simplified planar geometry, so the classical Rayleigh-Benard setup. We're considering convection-driven flows. Boussinesq fluid, it's electrically conducting. It's hot on the bottom, cold on the top. It's rotating. G points downwards. And our main driving parameter here is the non-dimensional Rayleigh number. Rather than go into the details of the mathematics, I'm just going to describe to you how we go about deriving the model, some of the basic assumptions that are going into these models. The first one being that the geostrophic balance holds at leading order. That is, that the Coriolis force and the pressure gradient force are approximately equal magnitude, opposite in direction. This is the leading order force balance. The other big assumption here, one I'll discuss more, is the horizontal length scale of the convection L. It's this classical Ekman-based length scale, so it goes like Ekman to the 1/3. This is the horizontal scale over which the geostrophic balance holds. And so this is an intrinsically anisotropic convection in the limit of rapid rotation. L gets very small as the Ekman number gets small. Does this work in DNS? Do we see the same length scale in DNS? It's valid to say, well, hey, that's a convection length scale. Does it really hold in dynamos? So these are results from a recent spherical shell dynamo simulation, one of the most extreme that I'm aware of. This is an Ekman number 5 × 10⁻⁸ from Schaefer et al., 2017. What you're looking at here are equatorial slices of the radial velocity component. during two different times. At one point when the magnetic field is relatively weak, at another point in time when the magnetic field is relatively strong. Okay, same simulation, rotation, we're looking down on the rotation axis here. You can see that when the magnetic field becomes relatively strong, kind of forms some quiescent regions in the flow, right? But if you look closely, you can still see that there's this Ekman to the 1/3 length scale present in the simulation still. And indeed, they calculated this. So they found their length scale, the azimuth length scale in the simulations, normalized by Ekman to the 1/3, right? They're plotting that as a function of the RMS B phi, the RMS value of the B phi of the phi component of the magnetic field, so the longitudinal component of the magnetic field. Each of these green dots shows the length scale at a particular time, right? And what you notice is that there is a trend with increasing magnetic field. This length scale increases slightly, but this is perfectly valid within the asymptotics that I'll discuss today. This is not an asymptotic variation away from the Ekman to the 1/3 length scale. It is merely an order 1 change. So the asymptotic models can handle this. So what do we do? Just briefly, you take all of your dependent flow variables, you take a perturbation expansion, the small parameter here, epsilon, is our Ekman to the 1/3, okay? Then you plug them all into the governing equations. As with you do in any asymptotic model, you collect all the terms of equal magnitude, and then you close the system out. And what you end up getting, and I'm not going to show the equations, is that you get two scalar equations for the dynamics. So from the momentum equation, you're able to reduce the system from 3 velocity components and pressure down to just 2 scalar equations, because you can relate pressure to the velocity field. Pressure is the geostrophic stream function. In addition, you can do the same thing for the small scale magnetic field. You get 2 scalar equations for the small scale magnetic field, namely the vertical component of the magnetic field and the vertical component of the current density. Then you also get a vector induction equation for the mean magnetic field. In all these models that we've derived, they're all intrinsically large-scale dynamos, in the sense that you wouldn't have a dynamo if you eliminated either the large-scale magnetic field or the small-scale magnetic field. Turns out that you can derive 4 variants of this model in this limit of rapid rotation. These depend on the small-scale Reynolds number, RE, and the small-scale magnetic Reynolds number. So these are Reynolds numbers based on that small Ekman to the 1/3 length scale. Turns out in the asymptotics, these are the parameters that characterize the relative sizes of various terms in the governing equations. Each of these limits, these 4 different limits that you can consider, is associated with a specific magnetic to kinetic energy ratio, M. So even before you actually solve the governing equations, you're able to predict something about the flow. So you get some theoretical advantage by doing this. This is a plot showing that ratio M, the magnetic to kinetic energy ratio, versus the Rayleigh number. And what I'm plotting here is the asymptotically scaled Rayleigh number, or the reduced Rayleigh number, scaled by this classical Ekman to the 4/3 scaling. And so each of these 4 distinguished limits, these 4 different variants of the model, are shown by these lines here. And essentially, the most generic one is when Reynolds is order 1 and magnetic Reynolds number is order 1. So DNS is kind of stuck right now, at least, in these 2 parameter regimes. Okay? And so this is the only comparison that we can currently make with DNS. Turns out the predictions from the model agree extremely well with DNS. Just taking some data from Stelmach and Hansen. They did 3 different cases, simulations. This is the magnetic to kinetic energy ratio for these 3 cases, 2, 11, 28. Our predictions are 1, 10, and 30. Pretty good, considering. So we believe there is some truth to these asymptotic models. Some of the stuff that we've done thus far, aside from deriving the model, we've looked at some kinematic dynamos, some simplified single mode type dynamos where you just you take a fixed horizontal wave number, just one horizontal wave number. Look at those dynamos. Meredith recently published this work. Most of the work I'll talk about today is these two regions down here, some magnetoconvection studies that Stefano did, as well as some more dynamos later on in the talk. Okay, so the first thing that we've been doing dynamically with this model is looking at magnetoconvection. And so we impose a mean magnetic field of this form. Okay, so it's a large-scale horizontal magnetic field and it permeates the fluid. Why do we take such a field like this? Because it turns out that fields like this are produced by the dynamo in a Cartesian plane layer. So we wanted to make the closest connection that we could between magnetoconvection study and the dynamos that we're doing now. And in fact, this field here was produced via a dynamo. Now that we're imposing a magnetic field, we have an additional non-dimensional parameter. Nick mentioned it, it's the Chandrasekhar number. Because we're in this asymptotic limit, we have another asymptotically scaled parameter. This is an order 1 parameter. So anything in terms of asymptotics that is order 1, this means that we can vary it in our simulations. This is a Chandrasekhar number based on the small horizontal scale of the convection again. We can relate it to the standard Chandrasekhar number based on the depth of the box, Q sub h. You can see it's a 1 over epsilon squared times Q tilde, so it's intrinsically a large value in these studies. In addition, all the results that I'll talk about today, we use the small magnetic Reynolds number limit, small PM limit. We really wanted to get a look at kind of a more physically realistic, astro and geophysically realistic scenario, as well as look at the limit where the magnetic field, the mean magnetic field has a significant influence on the dynamics. What do you get when you do these simulations? This plot shows the kinetic energy versus time for 3 different cases. The blue line up here, this is a Chandrasekhar number of 0, so this is just the hydrodynamic case. Here's a Chandrasekhar number of 0.2 and 1 down here. These are all the same Rayleigh numbers. So this is a reduced or an asymptotically scaled Rayleigh number of 160. This is one of the largest Rayleigh numbers we've done. It's a very strongly forced turbulent simulation. What you'll notice is that for the hydrodynamic case and this weaker magnetic field case, the kinetic energy grows with time. There's a long secular growth of kinetic energy over time. This is due to the formation of these large-scale vortices. So this is due to this inverse cascade that I'll mention. I'll talk more about. And you can see here, you still get this large-scale, you get this inverse kinetic energy cascade. For the weaker field, at Q of 1 quenches this inverse cascade, and you can saturate your kinetic energy. What do these flows look like? So again, Keith showed some of these hydrodynamic cases for comparison. This is a volumetric rendering of the pressure or the geostrophic stream function. On the bottom, I'm going to show depth averaged vorticity. I'll also refer to this as the barotropic vorticity. It just means a depth averaged quantity. You're looking down on the rotation axis. And for the hydrodynamic case at this Rayleigh number, again, this is a reduced Rayleigh number of 160, you can see the formation of this large-scale vortex. So it's anticyclonic here, cyclonic here. This thing drifts around slowly with time. With increasing magnetic field strength, so Q of 1, Chandrasekhar number of 1, you can see that what happens is that you break up this large-scale vortex, this dipole that's formed here, into something that is smaller scale. And here's the depth averaged flow here. Q of 2, you break it up even more. So it becomes smaller and smaller scale. So whereas the hydrodynamic case, so weak magnetic field limit, you have this very large-scale condensate on the left. Strong magnetic field, you actually push this barotropic flow into smaller and smaller length scales. We can understand this a little more in detail from the energetics. looking at the barotropic kinetic energy transfer equation. So this is the equation that governs the kinetic energy of the barotropic mode. So it's just the kinetic energy of the depth-averaged horizontal velocity, horizontal kinetic energy. And it evolves according to 4 different terms. This is self-interaction term. So this is the transfer function, the nonlinear transfer function between barotropic and barotropic modes. This is the forcing function due to the convection, so the baroclinic convection. This is the Lorentz term, and this is the viscous dissipation term. So this plot shows the transfer of energy to the kth barotropic mode due to each of these 4 different terms, and we show the sum as well over here. So Q0, you can see that it's dominated by this green curve here. So this is the baroclinic forcing term. And you can see if you sum these up, they sum greater than 0, and that leads to an increase, slow increase of the kinetic energy with time. Again, increasing the magnetic field strength for Q of 0.1, what happens is now you've increased L. So L over here, L is always dissipative in this case. Q of 1, what happens now is that you've shifted the peak from the dipole. So sorry, the dipole here is K of 1. K of 1, now you've shifted it to K of 2 here. Finally, at Q of 2, Chandrasekhar number of 2, what happens is you get this shift up to about a wave number 5. And in terms of the energetics of the barotropic flow, it's dominated by a balance between ohmic dissipation and the baroclinic convective forcing. So you get this nice balance here. We've developed a criteria for when you have this large-scale vortex, so what magnetic field strengths, Rayleigh numbers give you this value, give you this large-scale vortex. This plot shows the convective Reynolds number versus the Rayleigh number for all the different cases. So all these different Chandrasekhar numbers are magnetic field strengths. The blue curve here shows the hydrodynamic case. For hydrodynamic, for the non-magnetic convection, we get the large-scale vortex above a value, above a Reynolds number of about 10, and it forms here, right? But with the magnetic field, this is no longer a good indication of where the large-scale vortex forms. The other thing you'll notice is that the convective flow speeds, they're only weakly influenced by the magnetic field. So it's not just that the magnetic field's damping all the motion. It's actually disrupting the nonlinear transfers. A more useful parameter is the magnetic interaction parameter. This is Q over Reynolds. It represents the relative size of the Lorentz force to inertia in the simulations. And so this plot shows N, the intermagnetic interaction parameter, versus the Rayleigh number for all these different values of Q. The red dots show the simulations for which we identified a large-scale vortex, where this dipole dominates the flow field. Okay? And you can see that above an interaction parameter of about 0.02, 10 to the minus 2, sorry, you have no dipole anymore. So that does not dominate the flow. So the LSV is eliminated for interaction parameters for interaction parameter greater than about 0.02. So very weak magnetic fields can eliminate this large-scale vortex. I'm going to talk a little bit about some of the dynamo simulations that we've been looking at, carried out by Meredith Plumley. So instead of imposing a mean magnetic field, now we allow it to evolve. You get some richer dynamics, you get transfer of energy between the mean and the fluctuating magnetic field. So for the dynamo, you have to evolve this equation here. This is an equation for the mean magnetic field. This is our EMF here. We're in this low PM limit. In this limit, this is our small-scale induction equation. Okay? With this limit, you can write your EMF in this way. So in this particular limit, this represents an asymptotically exact form of an alpha squared dynamo model. Okay? What do you get with these simulations? So at low Rayleigh numbers, what we see is basically something that agrees more or less with the magnetoconvection simulations that we've been doing. What we find, so this plot shows the kinetic energy versus time. So the black is the total, and then we've broken up the kinetic energy into its x, y, and z components. The green is the vertical down here. So without the magnetic field, what you would see is this black curve just keep increasing. As it increases, eventually the magnetic field, the mean magnetic field, starts to increase. So you generate a dynamo. It saturates that large-scale flow and then quenches it down and stabilizes the kinetic energy. Okay? And so this is a Rayleigh number of 40. So for the hydrodynamic case, this is in the turbulent regime. It would form a large-scale vortex, but the magnetic field damps it and removes it. Similarly, we can look at the magnetic energy. So this plot shows the magnetic energy versus time. Again, the black is the total magnetic energy. And see, the blue is the y, red is the x component. So at relatively low Rayleigh numbers, what you tend to get is a magnetic field that oscillates. So this mean magnetic field just spirals around in the layer. And this was known from Childress and Soward from the 1970s. At higher Rayleigh numbers, you get something that's a bit more interesting. This plot again shows the magnetic energy versus time at a Rayleigh number of 90, so it's relatively strongly forced. And again, we're showing the total in blue, and then we've broken up the x and the y components into separate curves here. And so you can see that the magnetic energy has these cycles of growth, hits very high values. These are extremely large magnetic energies, grows, decays. Why does it do that? There's an interesting thing that happens. So as the magnetic field grows, what happens is that it forms a barotropic mode, and it orients it in a certain direction, in fact. So this shows the depth average stream function of the depth average pressure. And it aligns itself in such a way to minimize ohmic dissipation. During this time, the x component is slightly larger than the y component. So what you have are these magnetically guided jets that are more tilted towards the x-axis than the y-axis. During times of weak magnetic field, you don't see these jets at all. During times when the x and the y component of the magnetic field are approximately equal, what you get are these jets that are approximately at 45 degrees. This is what we would expect to see. Show you a movie of what's happening. So this shows a visualization of these simulations. So this is a plot of the magnetic energy on the top. You're looking at a depth average stream function, or pressure. On the right, this is showing the temperature field in the midplane of the layer. Okay, I just wrote baroclinic to remind you that this is a three-dimensional field here. Okay, so you can see that what happens is that the temperature, small scale fields are aligned by these depth averaged motions, these jets, in fact. And then what we find out is that there are barotropic instabilities that are developed by these jets. And there's this constant feedback mechanism between the small scales, or the fluctuating scales, and the depth average scales. How does this work? Well, you can kind of look at you can figure this out just by looking at the evolution equation for the barotropic vorticity. So if you take your vorticity equation, you depth average it, it evolves according to a forcing function, the convection, the Lorentz term, and the dissipation. So here, this is the axial vorticity decomposed into a depth average and a fluctuation. In the small PM limit, what happens is that you can show that this term here is proportional to quantities that are quadratic in the magnetic field. And so if you simulate this thing long enough time, what you'll notice is that the jets will form in this 45-degree angle on average. That's what we've observed here. So what we're finding, if you can drive this flow strong enough, we see a mean field that grows. It aligns the barotropic flow. This barotropic flow develops instabilities, and this leads to a net decay of the mean magnetic field. To wrap up here, what we found from these asymptotic models is that the magnetic fields, even very weak magnetic fields, they have a fundamental influence on the convective dynamics. And we can suppress these LSVs entirely. For very strong forcing, we've found these dynamo cycles. And I should say that similar cycles have been found in direct numerical simulations as well. The jets, the barotropic flow, no longer plays a very passive role in the dynamics, but it directly interacts with convection. What we're doing now, looking at the order 1 magnetic Prandtl number regime, all the stuff I've talked about here is small magnetic Prandtl number. This should hopefully bridge the gap between these asymptotic models and DNS. And we're looking more closely at what happens within spherical geometry. Thank you.
Questions for Michael? No questions?
It was that good, huh?
You want to go up to the mic? Him first, and then you, Axel. Him first, and then you.
So Keith showed us how these large-scale vortices can have different types of manifestations when you have different domain sizes. Have you tried seeing that in the magnetic case as well?
We have not. Yeah, good question. Something for future study, but we've not actually looked at that.
Axel.
The dynamo cycles from the Bushby et al. Paper, they were occurring when you have normal vertical field conditions.
Say that again? Normal what?
When you have vertical field conditions on the two Z boundaries, that the magnetic field is normal to the boundaries, right?
Okay.
And so if you use other boundary conditions, perfect conductor, for example, you wouldn't actually see those cycles.
Okay. Yeah, it's something that we could definitely test.
Yes.
The simulations that I showed were for insulating conditions, electrically insulating.
Electrically insulating. Okay, does that actually, that's not perfect conductor then? It's insulating, it's the opposite. So it's
That's right.
Vacuum, you mean, right?
Yes.
Yes. Okay, so then that's good that you have similar cycles.
Yeah.
Any other questions? If not, let's thank Michael again. And could the next speaker come up? Oh, you got it? Already on it. Sure. So, is yours already on here?
Yep.
Or? Okay. Oh,
Tested it out.
good. She'll give you a 5-minute warning.
Okay.
Before it's 20 minutes, 25. Yeah. I'll let you. I'm not familiar with PowerPoint, so you can press.
Okay.
So this is Stephen Cranmer. He's going to be talking about corotating streams in solar and stellar winds.
Okay, thanks a lot. Is this on? Yes. Okay, well, thank you. As soon as this comes up, I can talk about my title. But first, I do want to thank the organizers for inviting me here. And I do want to say that I really enjoy these GTP meetings because they sort of force me, anyway, out of my narrow disciplinary silo and to hear about all these other interesting applications of a lot of the same physics that I think about every day. But it's great to see all these different applications, right? So I'll be talking about corotating, large-scale structures in hydrodynamic and magnetohydrodynamic flows, which is the topic of this meeting, but in these outflows from stars, right? The solar and stellar winds. So we'll talk about some of these interesting, huge-scale, solar system-size scale patterns that can emerge in, say, the solar wind. So there's all sorts of different types of stars, different types of applications. I'll just focus on two. I'm trying to find the best laser. I'll talk about the solar wind, which is the one we know the most about, of course, because we're bathed in it, we're embedded in it. And then I'll also say a little bit at the end about massive stars, stars about 10, 20, 30 times more massive than the sun, that we have observed for a little over a century now, that have very dense outflows, 10 orders of magnitude times denser winds than the solar wind. And they're also rotating several times more rapidly, right? The sun rotates once every month. These stars rotate once every 2 to 3 days often. So very rapid rotation, very dense winds, and the corotating structures that occur are a bit different than the sun's, but they share a lot of the same physics. So I can start with the sun, right? There's the solar corona. I'm sure you've all seen nice satellite images in the UV and the X-ray of the emission in the solar corona, right? The big mystery is, why is there this outer atmosphere that has a temperature of 1,000,000 degrees sitting on top of this cooler layer that's 2 orders of magnitude lower temperature, right? How does the sun maintain that state of affairs over time? That's the infamous coronal heating problem that we've had ever since we've known about the existence of the hot corona. And there's still a lot of debates in the community about what is actually pumping energy up into this up into the corona. There are aspects of it that we agree on, right? We agree about the source of energy, right? That really does have to be the convective motions beneath the surface. So that's where the energy comes from. And to heat the corona, you really just need to take about 1% of that energy, somehow transport it up to the coronal heights, possibly temporarily store that energy in the magnetic field as magnetic energy, and then once you do that, dissipate the energy, turn it from either magnetic energy or whatever back into random thermalized particle energy as heat. The magnetic field is an important intermediary just because observationally we see that there's a lot more coronal heating in the regions where there are stronger magnetic fields. So along with that mystery, there's also the existence of the solar wind, right? The well-known story, of course, in 1958, Gene Parker realized that if the sun really does have this high temperature, high gas pressure, and it's sitting in the coldness of space, right, the surrounding interstellar medium, the pressure gradient will want to make the gas in the corona expand. And he solved for a time-steady accelerating solution that really still forms the basis of our solar wind modeling to this day. And he only had a few years to wait, of course, till the early 60s when spacecraft went out and validated the existence of the wind. We can now also use telescopes to essentially observe the solar wind. I hope you can see the fine structures in this movie, right? This is a coronagraph image from the SOHO spacecraft. The white circle is the size of the sun, but we've blocked out the actual bright disk of the sun to see these structures. The movie is repeating, good. And you can see these faint structures coming from scattered light off of density irregularities in the outer corona and the solar wind acceleration region. And you can really see it, right? And there's been wavelet image processing to make the features easier to see, but it's all real structures in the solar wind. Right, so we're continuing to explore it. Of course, Parker Solar Probe just launched, named after Gene Parker, is going to actually go into almost the outer boundary of this image at a distance of about 9 solar radii from the surface. So we'll get direct measurements in there pretty soon too. I'm mentioning this, and I'm also mentioning the variability in the solar wind because that's what feeds into the corotating structure. Right? When you measure the solar wind over a long time, this is a year's worth of data taken at 1 AU at the orbit of the Earth. We see this variability in the speed of about a factor of 2, 2.5 to 3 or so. And this speed quantity really is sort of the organizing parameter that we've seen about the solar wind. Just about all the other temperature, density, elemental composition, different properties of the solar wind really do seem to be organized along with the speed. And it does seem to be sort of a bimodal distribution, right? There's slow and there's fast. In time, that's easier to see. If you were to just collect this all together into a single probability distribution, it's a little less easy to see. There's a single peak, But if you were to fit this with functions, you would probably use 2 Gaussians instead of 1. So an idea of 2 distinct sources of wind is one of the ideas out there. But there's also other ideas about the fast and the slow components of the solar wind being generated just by sort of a single parameter knob that's turned to various settings, right? And that notion has some physics behind it because of the solar magnetic field, right? It is thought to be the properties and the geometry and the topology of these magnetic field lines that are stretched open by the solar wind that seems to determine the properties of the speed at 1 AU, right? This thing on the left is a measurement from the Ulysses spacecraft that zoomed over the north and south poles and measured high speed wind over the poles, low speed wind over the equator. That's sort of the radial distance in this plot at a time when the solar wind was, when the solar magnetic field was sort of a dipolar configuration, right? It had these open magnetic fields that you can trace down to very unipolar positive and negative patches of magnetic field on the surface called coronal holes. The equatorial regions were more complicated of origin in magnetic fields. The colors in this plot on the right show you the one measure of the relative amount of areal expansion of the magnetic flux tubes coming from the sun, and that parameter seems to have a relatively one-to-one correspondence with the solar wind speed. That's one of our solar wind forecasting tools. But this all interacts with the rotation. That's the point of this. These fast and the slow streams interact with the rotation. I'm sure people have talked at this meeting a lot about differential rotation, right? We've seen the solar interior properties of differential rotation. But when you go up from the surface, there are also radial changes in the amount of latitudinal distribution of rotation, right? The photospheric strong differential rotation, slower at the poles and more rapid at the equator, gets sort of tamped down a bit when the magnetic field becomes the dominant force, say, in the momentum equation, right? When the Lorentz forces become strong and the magnetic tension wants to keep things rigidly rotating. If you measure large magnetic features in the corona, you get something from Larissa Christa last year, for example, that sort of has the same sense of the differential rotation, but has much less latitudinal variation. And indeed, once you start looking at space weather and the properties of the interplanetary medium, people don't even think that much about differential rotation. They just sort of take this average rotation rate that I show in brown here, the so-called Carrington rotation rate, that sort of is the average of what you see. And most things in interplanetary space do seem to recur with this Carrington rotation rate. So there's the rotation, and then there's its interaction with the wind. And I'm sure a lot of you have seen systems like this where the underlying rotation will distort parcels that are initially flowing in the radial direction and turn the underlying magnetic field lines that connect those parcels into these spiral arm patterns, right? This is the same thing that you would get with a garden sprinkler or a garden hose, and you start spinning around, right? If there's just one longitude that's launching the wind, but each parcel is still moving out radially, the pattern that connects them in the inertial frame will end up being a spiral, right? You can see this in MHD also. If you're in ideal MHD and you constrain the system to be co-rotating, to be time steady in the co-rotating frame, that means that if it's ideal, that the wind speed in the co-rotating frame has to be parallel to the magnetic field. And again, in the rotating frame, the wind speed has this growing backwards azimuthal component that if you look at the pitch angle, it generates this nice Archimedean spiral type situation. Now, observations show some departures from that. Oftentimes, when you look at the solar wind, it does seem to be underwound, right? It doesn't seem to be as tightly wound as you'd expect from this simple model. And Banishkevich et al. Showed that this is probably due to the fact that many of the field lines don't originate from the equator where we are essentially, but they originate at higher latitudes where there was a lower a lower differential rotation rate, and thus would have a lower pitch angle. So a lot of that does seem to seem to work out. But when we have fast and slow streams in the solar wind at different longitudes, then there's the opportunity for them to interact with one another. Right? This is the so-called corotating interaction regions that we see, and if you have a fast stream ahead of a slow stream, right, if I go back and show you that equation, the amount of pitch angle that you get in the Parker spiral is inversely correlated to the speed, so you get much more tightly wound spirals for the slow wind than the fast wind. If the fast is in front of the slow, the streams separate and you get a rarefaction region, but if the slow is in front of the fast, they collide and you get dense compressions and then eventually hydromagnetic shocks that usually in the solar system form a little bit outside the orbit of the Earth. Usually by Mars they get formed, but we see them sort of starting to form at the orbit of the Earth. And of course there's a 3D aspect of this too, right? If the magnetic field of the sun is this dipole and the dipole is tilted and you have the fast streams coming out from the poles and the slow at the equator, you get this tilted, warped current sheet in between the two polarities. And if you just look at the equatorial cut, you get these magnetic sectors of positive and negative polarity with the magnetic field lines undergoing their Parker spirals all the way in between. This is that sort of what they call the ballerina current sheet that gets formed with this warped lower boundary condition. Okay, that's sort of the basics of it. There are several practical reasons for understanding these corotating streams. At the maximum of the solar cycle, these streams aren't that important, right, for space weather, right, for all the potential hazards that the variation in the sun and the solar wind can give us. At solar maximum, it's the flares and the coronal mass ejections and the really violent things. At solar minimum, when those other effects are minimized, the corotating streams and the shocks and the near shocks at the orbit of the Earth that pass by the Earth's magnetosphere can actually cause the dominant effects of space weather at the minimum of the solar cycle. And there are all sorts of practical consequences from the Van Allen belts to spacecraft drag in the lower ionosphere and thermosphere that can occur too. But one of the other practical problems that CIRs create is that they make it more difficult to trace the magnetic field lines back down to the sun to find out where the solar wind came from, right? Because there's an inherent loss of information as these streams collide with one another. It makes it much more ambiguous to try to trace the streams back down. This is an example from a series of 3D magnetohydrodynamic models that Sarah McGregor did a few years ago, where if you look at if you do try to trace the field line from 0.1 astronomical units out to 1 astronomical unit, if there was no corotating streams, this would just be a 1-to-1 relation in the wind speed at the two different heights. But there's this spreading in the middle because there's this ambiguity because the streams have sort of shared their kinetic energy and they've blended together, and they make it a lot harder to know exactly where things came from. So I studied this a few years ago in a series of models where we tried to really look at the high resolution origin of these streams. We know that at 1 AU, a lot of this detail gets smeared out, but we wanted to study how does it get smeared out. So we took a very high resolution magnetic field map and we traced the magnetic field lines out into the plane of the ecliptic, or basically traced them from the plane of the ecliptic back down to the sun, and created a series of 600 or something individual solar wind models. And down here you can see the relative change of the distribution of wind speeds at 0.1 AU to 1 AU for just that collection of individual one-dimensional models, right? It's slow and then it's fast, and basically it's just the distribution ends up being just a copy of itself but accelerated a bit in wind speed. But then we put that into this two-dimensional model where we allowed the streams to form and to blend together and to erase a lot of the high-resolution structure. And the resulting distribution, I hope you can see it, is much narrower, much close, peaked around 450 kilometers per second, like the observations. And the slowest and the highest speed wind streams have sort of been eroded away. So this loss of information is real, and it's sort of the bane of our existence for trying to understand where a given wind stream came from back on the sun and what were its intrinsic properties before it got messed up with all this corotating stream blending. Okay, I think that's all I had for the sun, and I did want to talk about other stars. You'll all remember your Hertzsprung-Russell diagrams from Astronomy 101, I hope, right? This is the surface temperature versus luminosity of different stars. We've got the main sequence of stellar sort of adulthood in gray there, and the thin white lines show the evolution of stars from the main sequence to mostly becoming things like red supergiants and blue supergiants as they get older. The points here are all the stars that I could find that we've actually gotten reliable measurements of the mass loss rate of the wind. Basically, the mass loss rate measured here in solar masses per year. How much mass is being lost globally by the star as a function of time. The sun is down here at a paltry 10 to the minus 14 solar masses per year, which means it would have to live for 10 to the 14 years to totally evaporate from the wind, which it's not going to live that long. But you see that as you go up to more and more luminous stars, the trend seems to be for higher mass loss. For these hottest stars up at the top with mass loss rates of 10 to the minus 5 solar masses per year, it will lose a solar mass in just 100,000 years. Right? So that has a big effect on the overall evolution of these stars at the top of the HR diagram. And I'd like to talk about the ones up at the upper left here, the massive stars. Again, initial masses of 10, 20, 30 solar masses, radii similar, and much denser masses, 10 orders of magnitude, much greater in the winds. Now there aren't many of these stars. There are very few in the galaxy, but we do think that their dense winds are very important for the overall galactic ecology that you can think of, right? The overall loss of material back into the interstellar medium that eventually reforms new stars, and this whole life cycle of stars keeps on going. But the mass from these winds ends up being an important contributor to that. But the problem is, if you're thinking of Parker's model for generating the winds, these stars don't have hot million-degree coronas, right? They just have their surface temperatures, and the atmospheres are dense enough for radiative cooling to keep everything pretty much at the surface temperature of the star going out. So in the 70s, Castor, Abbott, and Klein worked out a model that still seems to work very well for explaining these winds. It's the photons, it's the radiation from these stars, because their luminosities are so high that actually the photons carry momentum, and because the atmospheres are so dense, every time a photon gets absorbed by an atom or an ion, some of that momentum gets transferred to the atoms and the ions, and that can drag along and accelerate an outflow of particles from the star. And they worked out that it's actually the spectral lines in the spectrum, these narrow regions where the opacity is very high, right? The ability of the photons to absorb is very high. They actually end up dominating the radiative transfer and the generation of these winds. So it's a really pretty fascinating theory. There's all sorts of nonlinear positive feedbacks in there about this line formation. And yeah, it highlights the ability that atoms actually have higher cross sections than things like free electrons due to these spectral lines for intercepting photons. So the interaction with the rotation is also an important factor for this, right? These stars are rotating very, very rapidly, getting close to their centrifugally critical or breakup rotation. So the stars can become oblate, they become distorted by the centrifugal forces at the equator. And because the radiation is so dominant in transporting the energy flux in the interiors, there's also this phenomenon of gravity darkening. Essentially, you could just think of it as once these stars become oblate, it's sort of easier for photons to random walk out the poles than it is for them to random walk out the equators. That's not the best explanation, but it seems to work. And the poles are bright and the equators are dark. We've seen this in eclipsing binaries, and we've observed it in plenty of stars. But because the poles are brighter, there's more photons coming out the poles. These radiation-driven winds will drive stronger winds out the poles too. So there's been thought. I worked on this for my PhD thesis ages ago, but we also think this might be applicable to some of the prolate evolved star outflows that we see, like Eta Carinae and things like that. More mass coming out the poles than out the equatorial regions. Okay, but then where are these corotating streams? That's the question. There was another observational puzzle from the 1990s or so that we think can be explained with corotating streams. When you look at the spectra of these stars, we look at spectral lines that are affected by the wind, so you can actually see the outflow in the wind. If you translate wavelength into velocity, you can measure the actual terminal speed of the wind by looking at how much absorption there is in these lines. But when you look at them varying as a function of time, they vary quite a bit, and if you were to stack up each spectrum on top of each other in time and plot it as a grayscale, you can see these dark absorption features sort of moving through the line from low velocity to high velocity. So these so-called discrete absorption components seem to be something like clumps that are accelerating through the wind, and you see extra density and thus extra absorption as they're moving through the wind. There are some stars with, say, radial pulsations that do seem, basically, it seems to be a periodic phenomenon, right? Each time there's an outward pulse, the star releases some extra wind, and you can see this outward pulse accelerating through the flow, and it seems to all make sense. However, many of the stars, if you were to measure their acceleration profiles, velocity versus time, it doesn't match with what the models say the stellar winds should be doing. So these features are not just passively accelerating out like leaves in the wind. They're doing something else. And part of the work for my PhD thesis was to follow up on Dermot Mullen's idea in the 80s that these were corotating streams, right? So instead of seeing clumps flowing out radially towards you, you're seeing different structures sweep by as they rotate, and you're seeing the radial quote-unquote outflow. You're seeing the material flow through these structures rather than clumps that are just flowing out themselves. And that seemed to work. Here's another one of these stacked spectrum comparing an observed star and a model that shows that you see very slow acceleration, and indeed sometimes you see discrete features that seem to be going up and then down and then up, or basically starting at mid-latitudes and then accelerating and decelerating. We called these banana profiles when we first saw them, and this corotating stream picture seems to work. There are still a lot of questions, like in order to produce corotating streams on a radiatively driven star, you need bright spots on the star to produce extra mass loss. Where do they come from? There are some different ideas about non-radial pulsations or magnetic fields that are still being followed up on. But then there's also even a more fundamental question about the intrinsic stability of these flows. If you really look in detail at these Castor-Revit and Klein equations, you find that the flows, that the radiation driving is really an intrinsically unstable phenomenon. The flows spontaneously produce a very narrow collection of shocks throughout the outflow in density and velocity. And these are just one-dimensional models. We're still working on 2- and 3-dimensional models where we still don't really know whether these large-scale corotating streams will survive when put in a field where these instabilities are allowed to happen. Okay, I think that is all I had. I just wanted to say that, these outflows from stars really are great test beds for studying, waves, turbulence, and large-scale structures in rotating magnetic fluids, which is the topic of our GTP. I didn't say much about waves and turbulence. They're fundamental to driving, I think, the solar wind, and they're observed in stellar winds as well. You can go back 2 years to the YouTube channel. I think the 2016 GTP talks are still up, and you can see my talk there where I focused on that. And again, I just want to emphasize that I really enjoy this sort of collaborative, interdisciplinary nature of these meetings where all these different fields can share their knowledge. All right, thanks.
Questions for Steven? Axel?
There are some hot stars that do have 10 to the 7 Kelvin coronae. Maybe those are just the gamma cast phenomena stars that you know about. Do you think those must all be generated by turbulent magnetic fields that could be generated in the subsurface ion bump convection zone?
Sure, yeah, no, it could be. Yeah, something like 10% of all O and B stars do have strong magnetic fields. These gamma cast stars are even a separate category that we still don't know a lot about. But there are other magnetic stars. that yeah, it's about 10% of them, but 90% of them don't seem to, and most of those are the ones that have these.
Could be correlated with the convection occurrence.
Yeah, certainly.
Ralph?
Steve, at what stellar masses do you see transition from these solar-type corona flows to these kind of line-driven winds?
Yeah,
And is that well understood observationally?
There really is a desert around maybe, yeah, three, 4 solar masses where we just don't see any kind of outflows. I do know and that's like the A stars, right? The late A, early F stars. I have seen some evidence for weak X-rays in A stars. I think Hans Moritz Gunther has been presenting some of that, but certainly not mass loss. Yeah, no, and in fact, a lot of these other stars that we have solar-type mass losses for, it's a very lucky coincidence that we have them because they're very nearby. The interstellar medium hasn't absorbed out their Lyman alpha profiles, and we see the interaction between, you know, as you take a line of sight between us and one of those stars, we see the solar wind, we see the heliopause, we see the interstellar medium, and then we see the asteropause where the stellar wind is interacting with the ISM, and we can measure something about those other mass loss rates too. But going up to slightly higher masses, there's just fewer of them nearby, and we just don't have them.
Eric?
I'm going to ask about the prospects for observing the time evolution of winds in the solar mass like stars. I know there's only, at early times, there's only a few constraints on the actual mass loss rates, despite the high X-ray luminosities and such.
The young
yeah, the young ones,
type stars, yeah.
Or even, yeah, like as they go up and become high X-ray luminosities, we don't have a good handle on the actual mass loss rates from the winds at those times. Is there any prospects for improving the population of stars for which that can be measured?
Well, if optical interferometry could ever get off the ground, right? This old idea of stellar imager, right? You know, a constellation of optical interferometry satellites that could really resolve, you know, surface features. That would do a better job. For things like T-Tauri stars, we see signs of outflows that can be translated into mass loss rates, but we still don't quite know how much of that is actually coming from the star itself and how much is just being lost by the inner parts of the accretion disk.
It looks like Yuri has a question. John, if you want to start making your way up.
As a wise soul about massive stars, what is your view of why 10% or 15% of the O and Bs have magnetism visible? Why so poor?
It could be a fossil thing, right? It's is it just the fraction of star-forming regions that happen to collect with just the right types of coherent fields, and the rest it all sort of gets jumbled around, and I'm not sure.
Maybe they didn't know about chirality.
People have just been going up here, but this is the red thing. I don't know if we have a. Alrighty. You could try that. I'm not entirely sure. Yeah. All right. Well, let's thank Stephen again.
I turned it off.
Okay. Yeah. So green for being on. Yeah, that looks good.
Okay.
All right, so it's my pleasure to introduce John Hawley from the University of Virginia. We'll be talking about tilted black holes, tilted accretionists around black holes.
Yeah, it does say black holes. All right, so this is a problem that's been around now for 40 years at least. When the seminal paper by Bardeen and Pedersen in 1978 pointed out that an accretion disk around a rotating Kerr hole, if it was misaligned with the rotation axis, if its angular momentum was misaligned with the rotation axis of the black hole, then basically there would be a process by which the accretion disk could come into alignment with the equatorial plane of the black hole. And so 40 years later, this is a process that still contains considerable mystery, mostly because the nature of the process itself is inherently dependent upon the dissipation properties within the accretion disk, which are still being investigated. All right, so here's an artist rendition of an accretion disk. At the simplest state, an accretion disk is nothing more than the combination of gravitational attraction and angular momentum. Accretion requires that you somehow manage to remove the angular momentum so the gas particles can spiral in. Basically, accretion disks occur throughout all of astrophysics, everything from quasars to planets, planetary systems, perhaps even disks around planets themselves that lead to moons. So, the basic physics are very straightforward. It's what's going on, but the details are relatively complicated, and the observations are difficult. And it's good for the complexity because that gives us lots of things to have do research on and talk about. All right, now, there is no particular reason in general why the angular momentum direction, the vector for the angular momentum of the disk would necessarily align with the angular momentum of the black hole if it's accreting into a black hole. It's also the case that accretion within a binary system, the accretion disk might, under certain circumstances, not be aligned with the orbital angular momentum of the binary system. Anytime you have a non-Newtonian gravitational field with this so-called gravitomagnetic term can produce a torque on the disk. The question then is, under what circumstances does a disk become aligned with its angular momentum become aligned with that of either the binary system or the spin of the black hole? Okay, so the idea then is in these systems, tilts make torques. The torque is basically proportional to the cross product of the two angular momentum vectors. It drops off rapidly with radius. And if you consider the test particle trajectories around a black hole where the angular momentum of the test particle is misaligned, the test particle will basically precess around the black hole's axis. So here we have an example of a 12-degree tilt. And so as the particle orbits, its orbital plane will slowly precess, and so its misaligned vector will move around. If this is the z direction, it will move around. The x, y's will change, but like a top, it's not, it doesn't just stand up. The precession rate drops off very rapidly, again, as 1 over r cubed. So differential precession is induced by this torque. And so if you want to have alignment, what you need is for the misaligned angular momentum vectors to basically dissipate. And so you need differential precession. And so as you go out, this vector in the fluid elements will be moving like this. And so as you sort of think about blending them, then eventually you cancel out the non-aligned portion and you end up with an aligned disk at the inner edge. So the reason this hasn't been straightforward is because the process fundamentally relies on angular momentum transport in radial direction and dissipation of the misaligned angular momentum. It comes right back to these same sort of issues which Eric Blackman reviewed very nicely in the first talk today, which is the nature of the dissipation within the accretion disk. All right, so that's the key question. What is the nature of the disk alignment? And now, the way this has been approached for the last 40 years, by and large, has been through the use of an alpha viscosity. Now, in some sense, this goes even, it's even worse than using an alpha viscosity in the sense that the actual assumption being made is that it's viscous. Okay. Now, this is a joke. You can go to an accretion disk meeting, and the person up there giving the review talk will say, Now, we have known, since 50 years ago that the actual viscosity, molecular viscosity of the accretion disk is far too low by orders of magnitude to possibly accomplish the evolution of the accretion disk. So that is why we actually have to use alpha viscosity. And so the point is, alpha viscosity has now become another physical thing. It's not molecular viscosity, it's alpha viscosity. It's still represented by a scalar nu here. And in these analyses, it's generally treated as an isotropic viscosity and treated like an actual viscosity. Now, I don't want to be overly critical because, frankly, it's very difficult. Over the last 40 years, it's very difficult to make progress without some sort of simplifications. And simplifying to a viscous fluid using 1D average models is a way to make some progress. And so, people have learned aspects of the problem. But rather early on, it was realized that alpha alone wasn't necessary. It wasn't sufficient. It is necessary but not sufficient. And so they introduced another alpha. The reason is that when you think about what's happening, the disk is bending like this as it goes out. And so the dissipation depends on the stress in the vertical direction more than the stress in this direction. And you could assume they're isotropic, but then that wasn't completely satisfying. And it turned out that you sort of needed to introduce an alpha sub 1, or in fact, there are ones that introduced alpha sub 2, and the trend is continuing. All right, so question then, what really is alpha? The original Shakur and Sunyaev model, which we did hear a bit about this morning, basically just said that this stress term TR phi, or tau sub r sub phi, was proportional to alpha times p. So alpha in this sense is more like one of those dimensionless numbers, which is just giving you the ratio of the r phi stress to the pressure, which is the thermal energy in the gas. It's a perfectly reasonable assumption. And just simple dimensional analysis tells you that alpha should be on order 0.01 to 1. Now, we have recently decided that, at least I have decided, that the source of the accretion stress, that is the R phi component, is due to magnetorotational turbulence. And now, again, referring back to Eric's talk this morning, magnetorotational turbulence does not equal viscosity. And in fact, there's this paper in 1999 by Steve Balbus and John Papalouizou, where they looked at what you needed to have in the disk in order for the alpha model to be sort of justified. And basically was you need things to be sufficiently local that the same components of the Reynolds and Maxwell stress that is transporting angular momentum also enters into the energy equation as the thermalization of the energy. So you can't have non-local transport of heat or other properties. All has to be very local. And that probably works under some circumstances, but it's not general. In 1999, our review paper, we made this statement, which was, the viscous formulation is quite popular because it turns a turbulent fluid into a standard Navier-Stokes system, and the equations beckon rigorous analysis. This they should be denied. For those of you familiar with Steve Balbus, there may be one or two of you out there, you might be able to recognize his hand on that quote. But the key point is that a large Reynolds number turbulent disk is not a laminar disk with a much smaller Reynolds number. So that's a fairly straightforward observation. That doesn't mean that the analyses one does in that limit are worthless, but it does raise the question of whether or not what you learned there, it actually works. All right, so some recent years ago, Julian Krolik and I and a number of other collaborators started a project where we were going to do simulations without an added alpha, without assuming any viscosity, and just doing MRI-driven MHD turbulent disks, which were misaligned with the black hole. Now, a number of people have done these, particularly Christopher Gill has made a lot of simulations with a fully general relativistic potential of relatively thick disks around a spinning black hole. And so it's not like people aren't doing this. But what we decided to do is take a very experimental and idealized approach to the problem, and in addition, contrast MHD simulations with pure hydrodynamic inviscid simulations, which have no accretion stress. We decided to simplify gravity down to the Newtonian plus a linearized form of the gravitomagnetic term. So it gets rid of and then once you're in that sort of framework, you can fool around with the magnitude of the torque. You just turn it up or down as you like. So it's a very much an idealized numerical experiment where you can adjust the parameters to try to figure out what's going on. And the goal was simply to try to elucidate the physics of the process, compare it with the ideas that came out of the sort of more viscous analysis, and just basically try to understand what's going on. Okay, so here is an example picture of a simulation. On the left is a turbulent disk with no torque. We set up a disk, we put seed magnetic fields in it, we let it evolve for a bunch of orbits until it became turbulent, and with the usual sort of properties, accreting as it goes. And then we switch on the torque and then allow it to evolve forward. And you see here after, this is 15.2 orbits at the fiducial radius, which is r equals 10. You see that the inner disk has become a line. This line here shows the equatorial plane corresponding to the tilt. And then there's a transition region here, and then an unaligned disk out here. Now, the first thing that sort of comes out that is relatively obvious is that MRI-driven turbulence is not isotropic. Stresses are not isotropic. MRI favors the R phi component, and if all the simulations everybody's done with shearing boxes and other things, you always have this scaling, B phi greater than BR greater than B theta. So what we did was look at a cross-section of the warped disk, so it's going below and above the black hole equatorial plane, and look at the Maxwell stresses inside there, and they're basically, there's as many positive Maxwell stresses as there's negative Maxwell stresses. And there's nothing special about that direction for the MRI. It's not unstable in that direction. So if you have fields, they just sort of go like this and act more like a strain rather than a stress. A second result is that, and I'll say that I'm perhaps slightly disappointed by this, but the alignment process is dominated not by magnetic processes. It's, you say, okay, magnetic fields do everything, right? And so they're going to do the alignment. Well, it turns out that the largest forces are simple pressure gradients in the radial direction that come about because as you bend the disk, you no longer have the simple pressure balance in the radial direction. So, fluids move. So it's a bulk Reynolds stress that's really what's important. This is the magnetic pressure force, which is much smaller than this simple pressure force. And the stress, Maxwell stress, is even less important for this. So that's punchline one, is that I was hoping to be able to say at the end of this that MHD was absolutely essential to the process, and it turns out that you don't need it. It's helpful, but it's not actually essential. What MHD does is create turbulence. And the role of turbulence is not insignificant in the process, but it's not the transport of angular momentum by MHD that is the dominant process. It's the transport by bulk fluid motions and dissipated in shocks. Okay, so a diagnostic is simply to compute the alignment angle on spherical shells by averaging the density average angular momentum and seeing which direction the net is pointing. And so this is a disk that was 12 degrees misaligned initially. You see it goes up to 12 degrees here at r equals 25. There's this smooth transition region, and it becomes more or less aligned at about r equals 10, and you see that in the picture there. The inner disk is aligned, but there's this big, smooth transition region and then an unaligned outer disk. Okay, so here's the basic ideas. The angular momentum that changes the disk orientation comes from the external torque. That's the only source. The angular momentum that's put into the disk in the inner regions is carried outwards by radial fluid motions by the disk warp. The angular momentum delivered by the external torque can contribute to alignment only if the precession phase changes. That is, you need differential precession so that this misaligned vector is, it doesn't help to move the same fluid into another region where the vector is in the same orientation. Discovered fairly early by people doing simulations, various types of simulations, largely, was that this can be all brought to a halt by the onset of solid body precession. In fact, differential precession doesn't necessarily last. Internal motions, internal waves bring about solid body precession, which can bring the whole alignment process to an end. But otherwise, the alignment will cease when the rate at which the misaligned angular momentum is being brought in from the outer disk versus the aligning angular momentum being brought from the end. When those two match, then you're done. So we constructed basically a diffusion model by considering the velocity of the outward going alignment front, which is basically proportional to a velocity that you make out of the lens Turing precession rate, so r omega sub precess. And these factors out here, this is basically an integral of how much mass has how much angular momentum at what radius. And then this is an angle between the angular momentum vector that's being transported and aligned versus misaligned. So alpha, or the gamma, basically is pi over 2 if there's nothing misaligned, and 0 if it's not. So and then the inward diffusion speed is then set proportional to basically on dimensional grounds, simply the sound speed squared divided by the orbital velocity. And so the question is, what are these coefficients out front? But at the end of the day, what you get is, and this is true for any sort of diffusion model of the process, it's purely on dimensional grounds, that the sound speed, the radius of transition goes like the sound speed to the -4/5. There's some stuff out here, which is the constant of proportionality. And this stuff, in various people's versions of this theory, in particular if you go back to a paper by Nelson and Papaloizou from 2000, they looked at various models for that depend on alpha one way or the other. You'll notice there's no alpha here. So in our models, we decided we would look at isothermal disks, which are not particularly realistic, but which fixes the sound speed and then takes that sort of out of the equation, the dependence of sound speed versus radius, and then see what we get. Do we get this? Are we satisfying this prediction of the basic diffusion model? So here's 3 misaligned Keplerian disks. H over r of 0.1, H over r of 0.05, H over r of 0.035. So this is a reduction of sound speed by a factor of 2 and then a factor of square root of 2 because it was too difficult to go to another factor of 2 because of the resolution requirements. If we look at a plot of the space-time evolution of the alignment angle, blue here is the aligned region of the disk, and red is the unaligned region of the disk. And so let's take this example here, which was the intermediate case. The alignment front moves out through the disk and then stalls, and then it rebounds a tad. Same thing happens here, goes out, stalls, and rebounds to a steady state. Superimposed there, if you see it, is a line which is a velocity proportional to r omega precess. So you see that indeed that does go out at the velocity we thought it would. And then the thinner case, because of the using up all my time on the computer that didn't run quite to a steady state. So that line there shows the outward going alignment front moving at the predicted, proportional to the predicted velocity. In these three disks, you can measure alpha and alpha by computing the Maxwell stress over a vertical average and then dividing by the pressure, and then so that gives you so in these guys, alpha goes from 0.03 to over here, I guess 0.2. So alpha is large compared to h over r, but that turns out that doesn't matter, even though that's what people thought. Here is the late time alignment fronts. So with the different sound speeds, you see it does move out. The dashed lines are taking the higher sound speed one and moving it out to a position that would be where it would be if proportional to the sound speed to the minus 4/5. And so they align pretty good. And if we make that a little more exact by looking at the position of a point in the alignment front, and then plot the curve for CS sound speed going to the minus 4/5, you see that it works pretty well. Now, when we do the same thing with purely hydrodynamic disks, for the low sound speed case, that looks a lot like the MHD case. The intermediate sound speed case sort of looks like it, but it oscillates more. It also, you can see these waves in there, which are basically internal bending waves that are just moving back and forth through the disk. You don't see those in the MHD case because the turbulence actually disrupts the motion of the coherent bending waves. So that's one thing that the MHD turbulence can do for you. The biggest difference is this thickest disk, which starts to trying to align but then fails. And that's because another thing that these internal bending waves do is provide global communication throughout the disk to bring the disk into solid body rotation. And that's what ends the alignment process. So MHD delays that by disrupting these internal waves and allowing the evolution of the alignment front to continue. All right, so we can characterize the amplitude of the bending waves by basically taking the warp, which is basically the logarithmic variation with radius of the angular momentum vector. That's the direction, not the magnitude. And then normalizing it by h over r. Because if the warp is large compared to h over r, you're in a situation where the warp becomes nonlinear with respect to the thickness of the disk, and you expect dissipation. And so in cases where this basically is bigger than 1 by some factor, then you get alignment, but when it drops below, you just have the waves bouncing around, and they don't do much. There isn't any dissipation anymore, particularly. So this, we've seen then that the dissipation model works pretty well for getting the prediction of the transition radius as proportional to the sound speed in these simplified models. If we look at the fact that we set these up to have the same, same density profile and other factors means we were working with a sort of like in the sense of a partial derivative. The thing we were varying was simply the sound speed, but trying to keep everything else constant. The simple diffusion model doesn't account for the, it's like the oscillation of the front because we set it up to give you the point where you would have time stationary behavior so that it has its limitations. And the diffusion isn't the only thing going on. This evolution towards solid body precession is also important, and the distinction there is the diffusion will be local, but going to solid body precession is going to be a global process. And we can see that, for example, by the rate of solid body precession that it ends up with is determined by the averaged angular momentum of the finite sized disk. Okay, so the standard traditional picture divides these behaviors into diffusive, where alpha is large, and bending wave, where alpha is small. The discriminant is whether alpha is bigger than h over r or not. But in our simulations, we didn't care either way. We spanned a range, and there was no transition between one to the other. So what I would propose is a characterization in terms of alpha is not helpful. What is helpful is a characterization in terms of the warp amplitude and its relation to the thickness of the disk. So it's this amplitude in psi compared to h over r that's the key discriminant in understanding the behavior of the disks. Okay, so summary then. What have we learned? Despite my hopes, the process by which alignment occurs is predominantly a hydrodynamic one. The MHD turbulence does not produce isotropic stress, so in that sense it's quite different from a viscosity model. There is in particular no significant out-of-plane MHD stress. What is going on there is Reynolds stresses driven by bulk motions and shocks as they dissipate. We've seen that we can get a transition front between the two regions, and that does go as sound speed to the -4/5. And finally, that the thing that is the discriminant between the aligning behavior and non-aligning behavior is the amplitude of the warp relative to the thickness of the disk rather than the value of alpha within the disk, because the accretion stress itself really doesn't have much of a role to play. So a lot of this is part of a different take on the traditional model. The traditional model contains a lot of relevant, reasonable conclusions, but this is a slightly more precise way of looking at it. Okay, thank you.
Questions for John?
You realize it's, as soon as we're done here, you get to go to lunch.
So no questions, right? Mm-hmm. Any questions? I have a question, actually. So have you...
It's not necessary.
Yeah. Well, I was curious about, have you looked at the effect on jets at all?
Yeah. No, I haven't, but it's important because the bulk of the jet energy is believed to come from the spinning black hole itself. And so the ability of the disk to bring magnetic field to the black hole depends on whether the field is carried in a, so that it aligns with the spin of the black hole, and then you set up a jet that will be, constant and aligned with the black hole, not with the disk. But people who have tried to look at this in full GR simulations have found results that actually, in many cases, the magnetic field that gets carried in retains a memory of the misaligned angular momentum of the disk. And so you might get a precessing jet in that case.
Glenn?
Yeah, perhaps I missed it, but what is the role of the relativistic effects in this problem?
In producing the
And the warp, yeah.
torque. Yeah, it's actually there's two relativistic effects. One I modeled and one I didn't. One is that the space-time is not 1 over, the potential is not 1 over r squared, so there's an apsidal precession that just comes from the geometry of space-time. That's not included in this. The other is the so-called gravitomagnetic torque, which is due to the basically the angular momentum vector of the black hole, J cross the angular momentum of the accretion disk, L. So it's a proportional to J cross L and goes like 1 over r cubed. So it's just basically dragging of inertial frames by the Kerr metric.
Ralph has a question.
Observational test by which you could discriminate your model from the much more complicated models you talked about in the beginning?
You mean ones using viscosity? When somebody observes the exact location of a transition radius for a misaligned disk, then yes, potentially. Both models end up at the same place qualitatively, and so really you need to understand things a little bit better before you can make quantitative predictions about specific situations, specific disk thicknesses and such.
Yuri?
Just a little bit of background. Is the origin of the tilted disk really the properties of whatever was the nature of the binary star system that eventually led to your black hole and
Or it could be
companion?
the black hole spin doesn't line up with the galaxy material coming in from the, and it's feeding down into the black hole from the galaxy as a whole, maintains the overall rotation of the galaxy. But the black hole, we've seen with black hole mergers, GR numerical relativity mergers, you send a couple of black holes with different spins in, and there's almost no telling what you're going to get out. So the supermassive ones, there's no reason in the world why they should be aligned with the galaxy necessarily. And
But were you making a distinction between the supermassive and the modest?
Yeah.
I see.
Except size.
All are the same.
Yeah, it's relativity, right? It's all the same, right? It's all proportional to R sub G. And there certainly are, as people know, many cases where the jet doesn't look like it's coming out of perpendicular to the axis and the equator of the galaxy.
Any other questions? If not, let's thank John and all the speakers of the morning.
Check my laptop. Oh, right. This is the one that was already here, I guess?
This is theirs,
Okay.
yeah.
Yep. Yeah, already was.
I have a question.
Let's, yeah.
Okay. But this is yours, right?
No, it's fine.
That's yours?
Yeah, we've been going.
Oh, yeah.
Yeah.
Yeah, looks good.
have time?
Well, he ate some everybody.
Yeah.